Okay, so Johan, you are
Yes.
a carbon engineer of some carbon machining engineer, right?
Yeah, you can call it that. I'm not a composite engineer. I am working with developing machines for different companies. Right now, I'm employed by a company that manufacture carbon fiber weave. So I'm working with developing carbon fiber weaving machines and so on.
Okay, so just to give a little bit of backstory to people that are listening. So carbon fiber is a material it's not made of, it's not a solid material. It's made of components, and one of the components are actual fibers. It's called carbon fiber because it's made of strands of carbon, which are very, very fine and bunched together and then woven to make the carbon fiber product that we use or that we're used to seeing. So what Johan does is, in the short discussion I had with him previously, he's actually an engineer of the carbon fiber textiles, as in the fabric materials that are used in producing the carbon fiber sheets. Now, the sheets that are hard and solid that we know of when we look at our frames and whatnot, those are composites of resins, the carbon fiber sheet, and put together in various ways to get them to do what they do. Hello, Johan?
Yeah, yeah.
Was that all correct?
No, sadly not. We can start from the beginning.
Okay.
Most carbon,
Yeah.
when I say carbon fiber, I do not talk about the laminate that you normally refer to as carbon fiber. That is a carbon fiber laminate for me because that's a combination of the fiber itself and the resin system. And then regarding the weaving, we don't, in most cases, you don't use weave. Most part of a laminate is not weave, basically. There are exceptions to this, but in, yeah, nearly all laminates you see and laminates you have used are made out of UD, unidirectional
Right.
layers, meaning that they're not woven. And then it's just the outer layer that is woven, basically.
So this is supposed to be a very, very, very real conversation between me and Johan, but I'm also going to add a little bit more information here. So carbon fiber, the way you look at the carbon fiber, you see this woven surface on the top and bottom, but if you break the carbon fiber into pieces and you look inside, the inside layers typically in the materials that we use are not woven inside. They're just straight strands. And that's why you get shards of carbon fiber that are just sticking out and kind of fall off and get into your fingers. I have a lot of questions on that front, but also I wanted to point out that Johan doesn't work on making the physical fibers. His company, the entity that he works for, they actually buy the fibers and then weave them or work with them into the next stage product that is then used for creating the composites that are made for very specific applications, right?
Yeah, yes, exactly.
Okay, so the first question I have, which I'm really excited to ask, is there are fiber products that are like T300, T700, T1000. These are referring to the fiber strands, correct?
Yes.
So, is there a legitimate difference between a T300 or a T600 strands, and what does that T actually mean? Tension, torsion, what does that mean?
It's they're all from Toray. It's the
Mm-hmm.
world's biggest manufacturer of carbon fiber. It's basically their product name you were talking about. To be correct, T600 doesn't exist, not officially in their list anyway. But the most common names are T300 and T700s that we see in the drone industry. There are the name itself are referring to the strength, not the stiffness. We will talk about this more later, but names come from how you measure the strength in the American way of doing it. But the T300 is actually, if that will be manufactured today, they actually call it like T500 because they have made iterations of of it from like I
Mm-hmm.
think it was introduced in 1971 on the market, and then they have like made it better over the years. So now it's
Mm-hmm.
actually is stronger. So if you're comparing T700 and T300, the T700 is not more than twice as strong. But and that is what you might think of when you just see the
So
name.
how is the T700 stuff different than the 300 stuff? What's the physical property difference?
It's basically only the strength, actually. There are version of the T700 called T700G that is a little bit stiffer, but the only difference on paper is strength, basically.
As in the carbon bonds from link to link of, I mean, how can you make carbon bonds? I mean, they're all carbon cyclic bonds. How does that,
Now,
is there,
yeah, it's if you look at one single strain of this fiber, that is stronger itself. And this is the interesting part about how to make a stronger composites, because that's a very well-kept secret from the manufacturer itself
uh-huh,
or themselves.
that
So
is
it's
very
not the
interesting.
bond, yeah, it's not the bond between the different strengths, it's the actual strengths, the strain we're talking about here. So you
Very
can just
interesting.
take one and then measure that if you want.
So in the hobby category, I have tested all of the different strengths, all the different materials, and I personally have found minimal to no difference. And I believe that's because I'm probably not getting the correct, I mean, it's probably fake. People are selling fake fibers. Um, but if you were to actually test a typical carbon fiber sheet that we use to cut frames from, the T700 stuff should technically be stronger, stiffer, at the same weight density as the 300 stuff, right?
Both yes and no, because when you're testing it as a composite. When
Right.
the resin system come into action and the orientation of the fibers and how the layup is made, in which order the different layers are placed in this
Yeah.
laminate, and actually
Very
is
important.
in,
Right.
and in
Very
what
important.
orientation your part actually were cut in this laminate. And
But at its
because,
core, if you had two of the same sheet made the same way,
yeah,
the 700 should technically be stronger.
yeah. Um,
It's good. I like to hear
Actually,
this hesitation in your voice because that's what I found in my own testing. Because I'm like, yeah, okay, but is it worth
okay,
double the price?
yeah, we're directly coming to the, the core of this. When we're talking about strength and this number that everybody is tossing around, they're absolutely true, these numbers, especially if you buy it from Torre or whatever.
Hmm.
But the strength we're talking about is tensional strength. When you try to like pull it in from both ends
Hmm.
and try to break it. But that is the strongest direction for carbon fiber. General, we say that compression is always the problem, because generally carbon fiber
Oh,
have only about 60% of its strength in compression.
very interesting.
And the compression ratio is highly depending on the resin system that is being used. So we will
Very
come into this
interesting.
later on, because I've prepared some images that I will show you. But
Okay.
it,
I'm That's amazing. Okay, so I'm gonna just explain that back real quick because I want to make sure I understand it. So in a carbon fiber sheet, if you just take the sheet and flex it, one surface will be under tension and the other surface will be under compression. The top will be under tension, the bottom will be under compression, right?
yes, I actually prepared an image. I will send it to you directly so that you can see it.
Cool.
Uh,
So then the failure point is really the compression of the fibers, and so going with the stronger fibers technically is not giving you a whole lot more strength because both of the fibers suck at compression.
in theory, if everything will work, yes.
Interesting.
In our design that we have been working with, it does this. It breaks straight off. But the problems you have seen in your products, there's nothing wrong with them. It's just general.
Don't worry
Everybody has
about
the
it.
same
Don't worry
issues.
about it. Yeah.
They will actually fail because of shear. And now we're getting into complicated stuff. But if this laminate will work for an arm, as I shown in this picture, it should fail on the compression side first. But it do, in most cases, or I would say in all cases except with our laminates, it will fail in shear first, and then it will fail on some of the other sides. So it will look like it'll fail in tension, tensile, but it didn't actually.
So that's very interesting. I didn't even think about that part that far. I didn't know those properties of the fibers. But the other one thing I want to point out, which may make things a lot more complicated, is the twisting motion on the arm. The forces would be kind of all tension, wouldn't they?
I'm prepared that image as well, as you see here.
You're very well prepared.
Yes. Yes and no, actually. You will have a compression as well, but to handle the torsional forces on arm, you need to have laminate that is made for that. You might have experienced that if you have cut an arm out of a quasi-isotropic laminate. It might have been better in this torsional mode. Have you experienced that?
Yes and no. It seems to be maybe slightly better, but nothing significant.
Okay. Because to handle torsional forces, you need fibers that are 45 degrees plus minus on your laminates. I can show you an example.
So let's go over the laminates themselves, or let's go over the actual laminates themselves and how they're typically set up. You have the picture of all the cross-hatching. So while you get it, I'll explain. Carbon sheets are typically made of layers of actual fibers, and these fibers can be oriented and designed however which way the manufacturer wants them to go. Typically, only the top and bottom layers are woven just for cosmetic purposes. They also have strength qualities, but just they're mainly for cosmetic purposes and don't contribute quite as much to the actual final carbon product and its properties as all the other layers inside. So what you're seeing right now is the typical layup of fibers. So there's a lot more sheets in this, but typically the fibers, the lines on these arms are describing the direction of the fibers. And so the bottom one is going straight down the arm, while the next level up is going horizontal to the arm, and then it goes back and forth. And the top layer is just showing all of them kind of blended together what the cross-hatching is. It's a square 0-90 cross-hatching. Another way to do this is to, instead of going 0 degrees and 90 degrees, you can go 0, 45, then 90, then back to 45, then back to 0. And that takes away fibers from the length direction going straight down the arm and lends fibers to the 45-degree direction, which may or may not help with the torsional strain on the arm. But it does weaken the arm down the length of the arm. So it may break easier in the non-torsion direction, in the compression tension direction, but it will hold up better, hopefully, in the torsional direction. Is that right?
Yeah, exactly. And you're normally limited by this choice of two laminates, this 090 laminate or this quasi-isotropic laminate, as they're normally called. But what we have been playing around with is laminates that we have designed ourselves. So, because we know that
I have a couple other questions.
Yeah, okay.
So, sorry, a really interesting question that I need answered myself. So, how much of a role does resin play in all this?
For compression, um, quite a bit. For the shear forces with a regular laminate, quite a huge impact actually.
Okay.
But yeah, that's the problem you have.
So
So
right,
because
it's the actual resin. That's why the carbon fiber splits at the ends when you stub it against the ground or crash. Like the end of it is actually phrased, is because of it's because of the resin in it, right?
yeah, resin is very weak compared to the
The
carbon
fibers.
fiber. I think it's like the factor 1 to 50 or something like that. But
So
the
the
fibers
way,
have the fibers
yeah, the
have
fibers
only strength in one single direction. They're totally useless in all other directions. But the resin is, yeah, more or less
is what's holding
equal
the
in all
other
directions.
areas together. So then
Yeah.
the laminates or the pre-finished products, which are the pre-pregnated laminates, if you look at the edges of your carbon fiber arms and things, if you have a 5 mm carbon fiber, you might notice that you have 5 layers that look like they're glued together. And so that's because the carbon fiber product comes to the person that's going to be making the different thicknesses of a sheet in 1 mm thickness layers. And so if they want 5 mm, they just slap 5 of those layers together and cook them together. So the other process of carbon fiber making these sheets is that you put it together with the resin and then you have to bake it under pressure and heat. And you get everything to bind and then cure and laminate together. And so the resin, if it's not good quality resin, it will cause this delamination of the edges of the arms, or can potentially make the torsional twisting motion on the arm worse or weaker, and you can run into a whole bunch of issues there. So it's the resin and the fibers that are both important. The resin is important for different reasons. It also seems to help with the compression direction, which is very, very important as well. And so my next question to you would be: is the actual resin that's in the pre-pregnated sheets, is that inferior to the alternative, which is laying all the layers together and then blasting it with resin?
It's super hard to get, close to impossible. Yeah, I would say in reality, impossible to get the resin into a laminate that is that thick.
Aha.
You cannot get the flow to work. So it has to be in there to start with, especially if you're doing this under pressure. It
Interesting.
You can. Now we're getting to a point I don't really can talk about what's because I'm not sure what it's officially or not. But you can make a product that is possible to infuse that is way thicker. But then you have to, yeah, custom make or
A
modify
process to
the.
get the resin to get in there, right?
Mm, you can alter the shape of the fiber or how it's placed so that
How it's
it's you
arranged.
get. Yeah, exactly. So you
Channels through
can
it. You
get
get channels through it to get the resin in there.
exactly,
Interesting.
exactly.
Very
But
interesting. Okay, so then
but
one
that
last
is
question
nothing
before we
that
get
is
to yours.
interesting. It's nothing that is interesting for this product because in this case it's pretty straightforward with the pre-preg. The only downside with the pre-preg is that it's more expensive, but
Huh.
you get the resin there. And if you would have a laminate that were considered, I can't speak English, sorry, that were made out of layers that were 1 mm thick, I will say that that is a pretty bad laminate because you want as thin layers as absolutely possible. The
Oh,
thinner layer, the
really?
better. Yeah,
Interesting.
absolutely.
So you mean as in better resin penetration?
Now it's if the pre-preg it's already there, so that is not the reason. Um, if you have thick laminate or a thick layer, you have that because it's cheaper to make a thick one. But
Huh.
okay, you can have a thick one if it serves a purpose. For example, if you have zero direction that you want a lot of strength in, that is
Uh-huh.
far out, then you can have a thick one because of that.
Uh,
But if you want to get away with less risk of delamination or something like that, it's better to have a lot of thin ones, thin layers. But that is more
Interesting.
expensive, and
So,
that's why you
okay,
don't
so
have that.
the pre-preg is only in one direction.
Yes.
Okay, so that makes more sense. So the fiber, the actual carbon fiber product that I'm using in my own frames, my own recent frame designs, the layers are very, very thin, much thinner than what I'm typically used to seeing, and that might be what makes it feel so much stronger and feel so much better, and that also is why it's more expensive.
Yes,
Aha.
exactly.
Okay.
You're paying
So then
for...
one other last question. So one, sorry, one other last question. I'm really excited about this. The what is it called? The stuff that Lamborghini made that's used on some frames now.
Forged.
Yeah, forged
You're
stuff.
looking...
Yeah, what do you say? What do you think about that? What's your ideas?
The industrial name is called SMC. It's the forged. It's just a brand name. It has nothing to do with forged, like in forged metal or something like that.
Right.
It's starting to get popular nowadays. It's a lot of hype in the industry about it. One of the reasons is that you can reuse scrap material to actually make something out of it, so that you actually can sell the scrap that we get when we process the material. That part is actually really good when we're talking about environment stuff, so that yeah, you can actually make a material that you can sell with scrap that you normally just throw away. The downside with it is that it's made with what do you call it? You basically feed it into a chopper, and then you cut it in small pieces, and then they fall down on a conveyor randomly. So you don't really know how much fiber you get in a certain position, a certain spot of this laminate. So the solution is that you make really thick laminates, basically, because then randomization will solve this. The thicker the better, basically. The problem I'm assuming that the manufacturer behind Forged have is that in their process they are infusing the resin from both sides after that these have been chopped, basically, and put on this conveyor. And it's pretty hard to get an infusion to work in such a thick laminate. They might have solved it. I don't know how. I don't work for them. And if so, that's just really great. But that is the risk, that you can end up with too low resin content in the center of these laminates. Regarding properties, it's of course pretty close to isotropic in XY direction, not in Z, but it's relatively good in Z as well. So if you will have a laminate like that and compare it with something that is made out of UD and fabric, you will actually feel that it's lower in stiffness, and I don't know strength actually, but the ones I've felt anyway, they're lower in strength.
Yeah, that's been my experience as well.
Sorry,
no, it's fine. It's not, you can't predict the strength in anything. So you'll get two of the same part cut, but they'll have different strengths, and you can't predict what's what.
Yeah, but it doesn't need to be a bad thing. It has positive things as well. I think that one thing is the impact. It's really good for impact, and you can compensate for. Yeah, I don't know why, but in my colleagues that have been doing some research on this subject, and they said that impact is really good. It handles impact really good.
As in, like an arm sticking out in the middle of nowhere impact, or like a dome shape on like a car body, like the bumper of a car.
If you have a pig and then you like hit it really hard with like a hammer, a really pointy hammer, it handles that better. So your part have better strength afterwards, I believe. I'm not an expert. I haven't done this myself. I'm just
interesting. That might be because the forces are just being distributed everywhere instead of down any certain direction and being focused in a weak direction. Interesting.
Yeah,
Okay.
I'm not sure. We haven't done testing. I don't know. But it's not stiffer. It's not better mechanically.
So my experience with the forge stuff, I've actually tested it quite a bit. I've tried to get a refined product out of it. Is that it's drastically lower in strength. It can be improved, but it is very difficult to work with. The processing on it is very difficult to get it to the point where it's a smooth, finished, solid product that can even be compared to the regular stuff. And for some reason, I'm assuming because of the processing, it costs a lot more.
Yeah, it's so I really can't understand why people pay so much for it or why it's so expensive. Because the process of making it is not that hard. I would say
Really,
it's no.
my
Um,
manufacturer said the total opposite. But okay,
well, yeah, I don't see the problem really. I mean,
interesting.
you can Google the carbon fiber chopper, and you will find some Dutch company that sell choppers that you just feed in tow in it and just spray it out. And then you need to have like some kind of conveyor so that you can just spray it down to.
Huh.
And then you have to, yeah, the hardest part is to infuse the resin.
Huh.
And some interesting part is that I've seen now this big American manufacturer, Rockwest Composites. I will send you a link. I like this company. You sell like tubes and laminates and stuff like that. Then if you want better stuff than you normally use, uh, they have on their first page um, laminates made out of this, but that
Out
is
of
made
what?
out of
Oh, out of yeah.
SMC. They call it forged
Mhm.
as well. The cool thing is that they make it out of T800, and that is far better
Oh,
fiber than you normally use. The strange thing is that it costs as much as it do. I can't really understand that because they also have the option to have T1100 Vive in laminates, and that is just like one of the best fibers existing in the world. So
wow.
I will definitely go for that one instead if I were you.
For the
It's
same price.
even it's actually lower for the T1100.
Wow.
So I will
Very interesting.
definitely recommend you to go for that one. I mean, just guessing. I don't know. I'm
Yeah.
guessing this is leftovers from some airplane manufacturing
Wow, it's a lot
because
cheaper. Okay. So I have one other question I just remembered. Have you seen the woven thermoplastic, the stuff that uh, Toomey uses in their luggage?
um,
It's a woven, it's just like
uh,
carbon fiber, but it's a woven thermoplastic material.
no, I can't say
Wow.
I've seen it. It's a lot of hype in the industry
Mm,
with thermoplastics. In general, we can just talk general. Thermoplastics is superior to thermoset resin systems when it comes to impact resistance.
hmm
Um, another thing is that it's really interesting for being able to manufacture something fast. That's one of the biggest driving factors with thermoplastic, that you can just make it in minutes, just or even seconds if possible. The downside is that you never get as strong and stiff, especially stiffness with a
Right, yeah, because
thermoplastic
it's a
than a
plastic. Yeah.
thermoset. And
So
all of them are plastic, but the difference is if it's thermoset or thermoplastic.
I've been reading papers on mixing the thermoplastic with carbon fiber. So they'll do interlocking, not interlocking, but transitional layers, as in one will be thermo, one will be carbon, one will be thermo, one will be carbon. And they're
Yes.
finding like 20% reduction in weight for similar strength. And I was very interested in that, and I was trying to get my manufacturer to do that, but they can't bond the two together. Like apparently, the process of actually sticking the thermoplastic layer to the carbon layer is the problem, getting it to laminate together.
Yeah, I haven't heard anything about exactly what you're describing. The closest thing I've heard of is like thermoplastic films that you can have between the different layers of UD
Yeah.
layers. And what you're trying to gain with this is better impact resistance, meaning that after a high energy impact that actually deforms or destroy locally the fibers, you will still have a generally high strength left, and that works as long as I know. But you gain weight at the same time and you lose stiffness because these two different, or the layers, the thermal layers are not, of course, as locked to each other because of the thermoplastic layers in between. So they can move around a little bit. So you lose a little bit of stiffness, if I'm correct. I'm not super sure, but I think that is what I've heard.
Okay, now we can jump to your new product. Thank you for answering all my questions. Okay,
No
tell me about your new
problem.
thing. What are you guys doing? What's different?
We're doing a frame called MadKwads, and it's you can call it an A-frame. Basically, it's vertical arm design and has two arms from each motor to the main body or the pod in the center. This has been done before, but the problem with this design is that it doesn't work because it breaks the arms out of the motor all the time. And that was our experience as well. Then we contacted engineers at Textream that helped us develop a laminate that is totally different in its layup to compensate for this. And this totally solves all of these issues. So now it's like one of the really most strongest designs that we use over here anyway. And what we found was that this technology could probably be used in normal frames as you normally are running. And that is what I want to share, basically, what we found. And I think that this could be something that could actually make most other frames better if you, implement these technologies, basically.
Okay, what is there? Will you share the difference or how it's different?
Yeah, yes, absolutely. That's why we have this conversation. There are three major differences with our laminates and the ones that you normally uses. The one thing is that we're using a Textream outer layer, and Textream is also a brand. This fabric is called spread toe fabric, and it basically is a heavier toe. We need to try to explain, I believe, what is what a toe is and what a heavy toe is. But if you look at like a 3K fabric, that's pretty common. The reason why 3K is popular is because it's 3,000 filaments in every yarn, if you call it that, and that could be woven together to a fabric that is about 200 GSM heavy, meaning 200 grams per square meters. The problem with the 3K is that there are nearly only T300 made out of in 3K. Most better fibers are made only in heavier toes. So T300 is like one of the oldest, weakest, most flexible fibers that you can get. It's very well known, so there's nothing wrong with it. It's just that it's nearly 50 years old now, and there's far better fibers available on the market. A lot. I can send you a list so you can actually see what's some examples of this.
Huh, that makes makes a lot more sense. So then the carbon fiber products that are being used in industrial applications and like racing and whatnot are using way different fibers.
Uh, Both yes and no. Still, the T300 is super popular, but as you see here in this list, it's like the weakest and most flexible fibers of all. This group of fibers that it belongs to is called high strength carbon fiber, and that's just a more sexy name of a group that is also known as standard modulus fibers, meaning that it's just, yeah, every regular flex or whatever you call it. And then over this we come to like intermediate modulus fibers that is both stronger and stiffer, and next group over that is high modulus fibers, and then we are back at around the same strength but way higher stiffness. But here we started getting more brittle fibers. That is, yeah, it's not really super suitable for our drones because they take so much impact. So yeah, I wouldn't recommend those. But they're super stiff, like double in stiffness when you compare it to the T300. And then over that we have like ultra high modulus fibers that are made out of pitch, and they're just crazy. It's like what you made brake discs for Formula One cars or whatever, or tiles for like on a spaceship when you came into atmosphere and you have to have something to slow down so that it doesn't burn up. That's what you use that for. So it's super special, nothing that you would use for a drone, basically.
Interesting.
Yeah, but back to the T300. So that's just nothing wrong with it. It's just really old, and it's far better fibers existing right now. But it does not exist in 3K. But this means that if you read that, oh, this part is made out of 3K carbon fiber, it means that it's most likely made out of T300, and that is, yeah, the weakest.
Oh, I see. So it's synonymous with T300. The 3K moniker is synonymous with 300. Okay.
Yeah, more or less, yes. There are some high modulus fibers, but they are like 100 times more expensive. So no, there will not be those. And there can be T400, but I never actually seen T400 in reality. It's very rare. I don't know. It's just seen it in some data sheets, but I don't know about anybody using it. And then
so then which one are you guys using?
We are using 3 different fibers. We're using a UTS fiber that is in our weave. It's a little bit stiffer and a little bit stronger. It's similar to T700, a little bit better than T700, but
a little bit, yeah. It's 235 versus 240 and 5.3 versus 4.8. It's a little bit stiffer, a little bit higher tensile.
Yeah, in this list I sent you, the number for T700 actually is wrong. I think it's 4.9 in tensile strength in reality for T700. I don't know why it's wrong in this list, but that's the way it is. So that is this weaving technology, the spread tow, means that you're taking one of these these yarns with 12K or whatever, and then you spread it into a tape, very wide tape, meaning that it's get very thin. And then you can weave it with these tapes, and then you get a very thin fabric made out of these stronger and stiffer fibers without making a fabric that is super thick where your fibers are bent all the time. Because this compression strength that we talked about earlier on, for strength when you pull it, it's not that bad if you have woven it very thick, but if you weave and a thick weave, that means that the fibers have to just go over and under each other.
Yeah, yeah.
You're getting fibers that are not straight, and they're really poor for handling compression. So you lose a lot of the compression strength.
So this answers my other question, is that if you make a carbon fiber sheet that's like 3 millimeters thick with all woven layers, that's actually worse.
Yes, actually, it's better for shear, but it's worse for strength, and yeah, it will be very
interesting.
Flexible.
Okay.
I think actually some drone manufacturer actually made something like that. It
all
didn't
woven,
become popular. Yeah, I think I've seen one of those. Actually, it's very easy to see if laminate is woven all the way through or
right,
not.
You can look at the edge. Yeah, you just look at the edge.
Yeah, exactly. You see it, because normally it's really straight layers. It means that it's a UD, and there's nothing bad in that. If it's woven, it's more like wavy all the way through.
Yeah, yeah.
But you don't want that. One of the biggest purposes with having a weave on the outside is impact protection for the layers underneath, especially in a 3K fabric, because the UD is very sensitive to impact. So you want to protect it, and the weave is very good for that.
So then your product is it's a woven sheet, but it's very thin, so the fibers aren't deflecting much as they weave up and down.
Yeah, we only use this as our outer layer, and because the fibers, every square is like 25 millimeters.
Right,
in
it's
an
huge.
arm, it's like, yeah, it's not, if you're lucky, you can get one position without actually changing its position, and this entire weave is 0.07 millimeter thick in this laminate. So the angles when it's changing from top to bottom, it's just nothing. So basically, the fibers are going straight through in all, in this layer. So the properties of this weave is very close or similar to a UD, but half of the fibers, of course, are going along the arm, and half of them are going perpendicular. So that also means that because the fabric is thinner, you can move the next layer, the UD layer that is next underneath, further out without actually making your laminate thicker and heavier. Because in our laminate, the most important layers is actually the next one under. Because in that layer, we come to the next part, the number 2 thing that we made. And that is that we used an intermediate modulus fiber in that layer.
Very interesting.
So, yeah, and from what I know, I haven't seen anybody else actually using an intermediate modulus fiber in a racing drone before we did it, and I haven't seen anybody else yet. Do you know anybody that used an intermediate modulus fiber?
Arma 10 claims to be using some space grade carbon that they're getting off the backs of some company that isn't using them. But I have I can't even begin to predict anything about that.
No, it actually doesn't really tell you anything if it's space grade, blah, blah, blah. Because even T700 can be space grade or aerospace grade or whatever. It can
whatever it is, their system, their fiber, whatever it is, it has the big squares, which is it's similar to yours. It looks similar to yours in the sense that the woven cubes on the top layers are just bigger. But again, I have no idea what that means. There's no description or explanation as to what that means at all.
Yeah, I can actually explain what it means. They definitely used a heavier toe, but they didn't spread it. So it's not spread toe, it's just woven toes. Because
I see what you mean. So it's like 12K. So 12K is just bigger.
Yeah, I believe it can be a 12K that is just woven. And means that is a much thicker fabric than the one we are using. I will assume or guess that it's, I don't know, at least 200 GSM, maybe more. I don't know. But it doesn't say so much about what type of fiber it is. But anyway, in our product, that I can tell you, we're using a M30SC fiber as a UD, and it's oriented along the arm. And that is 294 gigapascal in modulus.
And the tensile strength is huge.
Yeah, I mean, if you compare it to T700, it's not that much better. I think it's 27% higher or something like that. I can be wrong here, but yeah, I think it's like that. It's 549 compared to 4,009. I'm screwing up my numbers here, but
wherever it is,
it's a little bit stronger, and yeah.
Well, compared to the T300, it's pretty huge.
Yeah, yeah, it's definitely better. Definitely better. But the only downside with the intermediate modulus fiber is the cost. Basically, it's both stronger, it is stiffer, and it's actually even better for impact than the high strength fibers. So the only downside is that it's twice as expensive for the fiber itself.
But you're only using it in 2 layers, right? Only the second layer on the top and bottom.
Yes, exactly. It's because the cost. I mean, our frame is pretty expensive as it is, and there will be no downside mechanically to have intermediate modulus fiber all through everything. It's just the cost. We need to check if somebody's actually willing to pay for it. But we want to be the company that sell products that are made out of higher grade of carbon fiber. So we're just checking the market if somebody's willing to pay for it right now, basically. So that's why we put it out on the market.
Interesting. Okay, so then what's the next layer? The rest of the inside.
Now we're at the third part of what we have done that is special, and that is the layup. So in this image, this is a generic image. It's not a frame, it's just a generic design I made. We're showing an example of how our laminate will look like from one side. It have way more layers than 5 layers, but this is just the outmost 5 layers to try to explain it. So outer layers is of course weave, as everybody has, but we have this trick string instead. Second layer is this zero orientation intermediate modulus fiber. And next after that is this plus minus 45 direction, that is actually T700 in our case. And those are there to handle
the twist.
Torsional. Yeah, exactly. And then we're back to 0. So we don't have the 90 degrees layers that you will normally have pretty high up.
I see. Interesting.
And that means that we can have more. We can have more fibers along the arm without adding the weight of the 0 or 90 degree direction.
That's so smart.
We can have higher strength with the same fiber. Yeah, with lower weight or whatever you want.
Yeah, you're just using the 90 degree direction in more useful directions.
Exactly. So this approach, you can do it with any fibers. It will be better, even if you have T300 or whatever, it will be better if you do this. But this laminate is useless to do anything else than an arm out of, because it has no strength in the other direction. It has, it
the
has
90 direction.
Yeah, exactly.
Yeah, but
so
it's
you
not
cannot
useful.
make a
It's not useful
strength.
strength.
Exactly. So it's actually pretty flexible. We made a video that will show how flexible it is. It's hard to describe it without actually showing it or feeling it yourself. But that's the thing, that everybody is limited to these 2 types of laminates that are commonly available. But because we made our own, then we can tailor this layup so that it's suitable for this, the forces in an arm, basically.
Wow, that makes amazing sense. Okay, so compared to your typical 3K or whatever I'm using, whatever most people are using, what's the cost difference? Because that's honestly the bit, and I'll talk about the cost after this as well. Is that's really the driving factor behind all this stuff? Because like I'll talk about it, but tell me what the cost difference is or the expected cost difference.
I would say it's twice as expensive, but it's
Hmm.
also hard to answer because I need to know what we're comparing with.
Right.
Because, for example, I tried to ask just for fun, how much will it cost to do something like this in China? Because
Hmm.
many of us are buying laminates from China. And then I started getting funny questions from the Chinese. And that was like, okay, you want T700. Do you want Japanese T700 or do you want Chinese T700? And was,
Yeah, I've gotten that so much.
okay, there are not made any carbon fiber in China, or they are made, but it doesn't exist a Chinese carbon fiber manufacturer. It doesn't just
Yeah.
exist at all. And the
Well, yeah, that
reason
just means
is,
it's fake. It's Chinese carbon fiber. It's just fake carbon fiber.
no, I can explain how it is. Most Chinese manufacturers uses Japanese fibers or imported fibers. So, I mean,
Okay.
if you have a part or bicycle or a hockey stick, whatever that is made in China, it can be definitely the real stuff. No question about it. It's many of the US big manufacturer of sport parts or whatever, they have their manufacturing in China, just like an iPhone is made in China. And it's the real deal. They imported everything, do it the right way. It's absolutely super great. But then when we're trying to get a drone made as cheap as possible, then you might not want to import that expensive fiber from Japan. So then they have this option to have this Chinese carbon fiber that do not exist, that you cannot Google or whatever. And the interesting part is how that is made, because the reason why China doesn't make carbon fiber is because they don't know how to make a precursor that is pure enough to make carbon fiber out of. The Chinese have guarded this secret pretty hard, so today it's mostly the Chinese, or the Japanese, sorry, the Japanese and Americans that know how to do it, especially
Wow.
the better qualities. Yeah.
So back to cost. And before talking about the cost, the other question I had was about molded carbon fiber and molded frames that we all love to look at, but it's a
Mhm.
question mark as to why, which I'll get to that in a bit too, because, um, well, how how does molding the sheets impact the strength and the all of this stuff and the cost of it? As in, you want to have a round arm, not a circle, but like a round arm, like the K-hole or the of any molded frame. Like,
Like
do,
the Exorcist or something like that.
yeah, something like that, right? That it's a shaped carbon. How does that impact everything together? Because it looks like they're using just the woven layer and they're shaping it, and that's it.
I'm guessing that they're placing this fabric as you're doing anything else, so that in this mold you're first placing a layer of fabric and then you're placing a lot of layers of UD afterwards.
Well, yeah, okay, so then it's the same kind of stuff. So,
Yeah,
what's the cost difference of molding carbon versus just the flat sheets?
it's a lot of labor involved, so if it's cheap labor like in China, then it's not that more expensive, but it's definitely more expensive. Um, yeah, it's
And it's
definitely more
much
expensive.
more it's also much more difficult to engineer as well because now you have to work with the 3D structure rather than just working with a flat structure, right?
Yeah, exactly. You need to
Okay.
make a very expensive mold. So
All right,
it's
so
your process will
here's
be
the actual
expensive.
explanation as to, I mean, I have researched so many materials, so many different materials, from spider silk to high density HDPE stuff, whatever, to thermoplastics, and so many, and the mixture of G10 with carbon, and the cardboard stuff with carbon, and the foam, like so many different types of materials. I just keep coming back to the same basic carbon fiber because I focus on design more than the actual material that I'm using. I just keep in mind that, okay, this is the level of material that I'm going to be using. It's a cost-effective material. It is what it is. It's this strength. It might get a little bit more if I get better materials, better carbon, but it's not going to become magical. I'm not going to find some magical material that's going to be able to make my crappy design better. So I focus more on the actual engineering of the design rather than the actual material that I'm using. And so I can cast my design across different materials and get different properties based on the material that I use. So the reason why I personally haven't moved to molded or shaped carbon or these weird structures of honeycomb structures and canopy structures and all this stuff is because the benefit aerodynamically, functionally, convenience-wise is not there. It's just there is not enough benefit to justify spending 4 times, 5 times, 6 times, 10 times the cost for one frame product. Sure, we have
Right.
professional racers at this point. We have professional leagues. Everything is professional, and people are willing to spend, $300 on a frame. That's fine if it performs and it's better and it's actually going to make a difference. But as far as I have seen, and as far as the market has come up to this point, there aren't a lot of people that can say that they're truly professionals or have reached the skill level where they can really push the equipment to the limit. Not just the frame, but I mean like the aerodynamics and the way the frame is set up to be able to give you these minor improvements. Plus, we have this computer code on top of everything, which is really doing all the work. So how much does the actual physical product make a difference with respect to what we're all usually doing? I mean, we're not all going 300 miles per hour. Sure, if you are, you need a whole lot of engineering. You need to do all that stuff to push those limits. But for the everyday person and the everyday race and the typical professional, there is just not enough benefit to go with a product that costs 5 times as much, 10 times as much, just because it might be a little bit more aerodynamic, or you might be able to get just a teensy bit more something or other here or there. And that's my rationale for it. That's my justification for it. Now, what you're doing, you've actually considered all this, and you've gone back and engineered something that makes sense. Is okay, it might cost twice as much, but hey, you're genuinely getting a better product. And in my opinion, reducing weight of the craft is much more impactful to handling, performance, durability, and longevity of the product versus trying to make it more aerodynamic or trying to get some other kind of advantage by weird arm shapes and locations and vertical fins and various things here and there. So that's why I actually chose to talk to you, because what you're doing actually makes a whole lot more sense. And when I first talked to you about your product, I was like, okay, well, there's another product that someone's trying to do something here and there, and it looks cool, looks interesting, but it kind of weighs a lot. And hey, they're saying it'll never break, but hey, everything breaks. And so then I learned that you're an engineer, and I learned more about the product, and I was like, okay, no, this is actually really interesting. And your claims that your frame does not break, that
No,
is
it's,
that
it does. It has.
legitimately it can break. Of course it can break, but the legitimate truth to it is that it is so far beyond engineered compared to typical frames and pretty much everything else on the market, that the claim that it is genuinely more durable, more capable in the strength department than other designs or other products is true. It's an actual truth to that, right?
Yeah, I definitely believe it. That is true, and I think that our customers can verify that is true.
And it's
We
not, and
sold,
you're also not selling it for 5 times the price. It's twice the price. It's reasonable.
yeah, because that is what it has to cost. We used so much different technologies that were more expensive in this frame to really try to push the technology forward, to try to learn something. And yeah, that's why it costs more. And we haven't even talked about the micro water jet cutting that we're using to make this, because
Oh
that
yeah.
is also a
So
big
if
factor
people are
why
still
it's so
listening,
expensive.
Right. They're using a water cutter to cut this carbon. So when you cut the higher strength carbons, as far as I know, your drill bits wear out way faster, right?
No, has nothing to do. Actually, a higher strength carbon fiber is easier to cut.
Because it's more brittle.
Yeah, but this is
So
not more
then it's
brittle. So we're not at that
right,
level.
yeah.
But if you're going really high, like in these high modulus fibers that we talked about earlier,
Hmm.
they're super easy to cut.
Because they can crack so easily. Oh,
Yes,
interesting. I mean, I'm
a
getting
little
different.
load
Of
on
course,
them.
I get mixed information from various manufacturers, as always. So so then why are you
That's not
cutting?
a
Why are you
reason.
using a water cutter?
We're using it because we have vertical arms, so we have slots where these arms go into the plates in the middle and out of the motors.
Uh-huh.
And we want this big contact area between these two parts these parts as possible. And if you do this with a mill, you need to make like a we call it a keyhole or something like that,
Right,
keyhole
right.
shape, because you have a radius on this mill.
Yeah.
But
Okay, so let me explain.
our
Let me explain that part. This is a very annoying issue that I have had to deal with, and it's the reason why you don't see a whole lot of designs that carbon pieces fit into other carbon pieces. So if you're trying to make a 90-degree angle on a carbon sheet, if you want to have a 90-degree corner, you can't because you have to cut this sheet with a round object. Your drill bit is a circle, and that circle has a radius to it. So usually it's 2 millimeters radius. They use 2 millimeter burrs to cut these sheets because it's kind of the most efficient size and gives you enough resolution of your radius of your turns so that you can actually get done what you want to get done. Now, I cut a lot of my stuff with 1.5 millimeter radius, which does cost a little bit more and does wear out faster, so that I can get a better, not just fit, but I also get better tolerances on my holes and shapes. But even if I still want to make things that interlock together, I'll still use a 2 millimeter radius for the interlocking part. And I'll have to make these weird U shapes and I shapes and whatever to get the parts to actually fit into one another with the processing that I'm using. Now, you guys are using a water jet so that you can literally cut a 90-degree corner in the carbon fiber. And that means that when you have a square piece that's slotting into another square hole, it actually fits into each other and you get intimate contact between all surfaces of this square of the hole and the piece that's fitting into it, and you don't have these extra spaces that you have to make just to get the carbon pieces to fit together and interlock, right?
yeah, something like that. It's still you still have a radius, but
It's
normal
very
water
small.
jet machine. Yeah, normal water jet machine have a nozzle of around 0.8 millimeter. We are using so-called micro water jet machine. They're extremely rare. So we are cutting with a nozzle that is 0.3 millimeter. So our radius is 0.15 millimeter. So if you
Holy
just, yeah,
crap.
it's so small that you can't nearly see it. It's perfect. And the cool thing is you can run it extremely fast. It's
Oh,
way
wow.
faster than anything else. Yeah, I think we have a feed rate of, it's crazy, like 2.8 meters per minute or something like that.
Wow.
Yeah,
I mean,
but
compared to a
the,
1 millimeter radius, that's what I
yeah,
usually use. The 1 millimeter radius, they're using point 0.15.
yeah, exactly. And it's, yeah, less than a third of that. So, and then we can cut way faster than you can do. And then, of course, all the way through at one go. So it's really fast when you're cutting. The downside with this technology is that it's super expensive machine.
Yeah.
So every hour it's costing a fortune. And every start hole is a problem because if you try to punch through, it will delaminate like crazy. So
Oh,
if you try to make a small hole, you need to make a hole, drill a hole first, and then start cutting in this hole to not get this delamination.
wow.
And you need to wait a fraction of a second before you start moving your nozzle because you need to start the feeder, sand feeder, because yeah, so that you have the mixture of water and sand correct before you start
Uh-huh.
moving. Otherwise, you get this delamination once again, and this takes yeah close to a second or something like that. And this second cost you a lot of money because you have so many holes. So yeah, it is expensive, even though it's super fast when it's cutting. So if you have long contours, then it's relatively okay. It's still expensive, but it's not that expensive if you compare. But if you want to make a plate with a lot of small holes like you normally do when you're cutting something like this because you want it to be as light as possible, then it's a pain.
Wow. Seriously, wow. That's amazing.
Yeah. And a cool thing that we haven't actually shown is how we get the tolerances correct between all the parts, so that all parts are, if you compare them, we're trying to like get the parts from one batch to fit into another one. And because these nozzles in this water jet machine, they wear, so they last for like 1 day or something like that. Then they're worn out. And during this day, this nozzle gets bigger and bigger. So you need to compensate. You need to rig this to compensate for this. So what we've done is that we made our own like a fixed guide that measure the width of these holes with like, it's like a tool. You sit down in it and put in it. I can't speak English.
You're doing great. Fantastic.
It's really late in the night here in Sweden right now. I'm starting to get tired. And then you can, the longer you cut, you will get this tool further and further down, and then you can see that, oh, now I need to reduce compensate like 2 microns more or whatever, so that we can be extremely tight in tolerance during these batches, so that one arm from one batch to another one will be super tight. So it's not like we don't test the parts to each other when we set the tolerances in this water jet. We test them to this master guide, so that all parts will always fit into each other, even between batches.
Wow. So a lot of effort goes into all this stuff. A lot of things that people take for granted goes into all this stuff.
Yeah, but that is the way we are. But the conclusion with all this is that we did this, even if you don't like the concept, we did this to try to push the technology forward. And what I'm trying to do now is to share this with this community, so that you might get some ideas that, we can take this and apply this approach in a totally different design. Like in the images I've shown here, they are just generic. They're not made for this frame itself. But I think it will work, and we will actually try now if it will work in a normal design as well. So I've actually ordered a laminate right now that is tailored for being a 4mm arm, but it's of course should be something that is more like a 5-6mm in strength and stiffness, just to cut some basic designs and even other manufacturers' design, just to verify if it's actually is better or not. And because of that, we made this test rig that I showed you before, so that we can make a real measurement of what is, how much stiffer or not it is.
Yeah. Very interesting. You're, as far as I know, as far as all the people I've talked to, you're the only one that's actually moving in a direction that makes sense for the industry, rather than just trying to look for some magical material that some manufacturer already makes, or looking to some extreme kind of molded, weird shaped carbon or something. This direction really makes sense. It makes absolute sense. With this general, just the layup design is, which is difficult to convey to any Chinese manufacturer. You could technically just drop an easy 0.5 millimeter off any arm or anything, or off any design, and retain the same durability.
I hope you can, yes.
So
I can't
in essence, it'd be like 10-15% lighter no matter what. Well, yeah, no promises, but it would make sense to just drop the other layers in the direction that aren't really doing so much, and that's immediately going to give you 0.5 millimeter of weight savings without any durability loss.
Yeah, that is what we believe in a way, and we think we've proved it.
Very interesting. Very, 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 very interesting. Very interesting. Maybe, well, maybe not. Maybe, hopefully, you guys can cut my design in this, and I can offer like your branded product, carbon, in this
Yeah,
design.
we don't need to be a frame manufacturer. We can just make arms for others if that
Yeah,
what manufacturers want. It's yeah.
and I would just have you cut the whole thing, the whole design, except, well, maybe not the main body plates, or maybe just some of the main body plates, because it would just get a little expensive. Maybe somehow try to manage costs. I don't know. We'll see. But yeah,
Or
that
make it as an
makes a lot of
option for the
sense.
customers so that they can
Yeah.
try it and compare it so that they can have the regular version and they can try the other version and see if
Well,
actually it's
that's
something
what I'm
better.
focusing on right now. So I have my my one acro design, which I've refined tremendously over the years at this point, and I have two racing designs, which I'm not expecting to change for years. Like nothing, not that much has changed for a long time in the industry, and I'm not expecting these racing frames to change either. They're all going to be flat carbon still 5 years from now. As far as I can tell, based on the previous 5 years, there hasn't been a whole lot of advancement. So I'm focusing on two primary designs. One is my independent modular arm design with the arches and whatever, so that there's some durability to the actual electronics inside. Then the other design is just the same old design that I've previously made that I honestly can't do better. I can't figure out a way to do better than that old design. So I just revamped it and refreshed it for the more recent the more recent components that we have now. So I'm
Mhm.
planning on keeping these three designs, and then I have my smaller toothpick design, which, holy moly, I could probably make it 2 grams, 3 grams lighter with your carbon, and it won't cost a lot because the parts are so small. You can cut a million of them on one sheet. Um, oh, that would be incredible. That would be incredible. And then I'm working on a cinematic design for 5 inch, and also a like a cine whoop design for 3 inch. And that's going to be my entire lineup, and I'm not expecting to change any of that for the foreseeable future. So then I can start playing with different materials and see what materials work better on various parts of the designs, and that's what is going to change moving forward, because the designs themselves to me are not that special anymore. There's every design possible has already been done. I've seen everything under the sun at this point, and I don't expect anybody to come up with anything that's drastically different or better in any way. Sure, you can make the orientation or the shape like this and like that, but like you said, your own design, the A-frame design, it's not an original concept. You've just blended that design with the engineering and the material that you've developed. So it makes sense.
Yeah, we made it work. Our design is different compared to the other ones I've seen anyway. The major thing is that the arms are attached to the main body in two different levels. And that
Mm-hmm.
means that the arms can actually cross each other without needing to be like having a slit in them that make them weak. And that
Yeah.
makes main body way stiffer. So the main body is strengthening the arms, and the arms are strengthening the main body. So it's pretty complicated design if you want to try to understand how the forces go through it. But it's yeah, just a totally radical design. But
That's
as
fantastic.
other have made arms with designs with two arms before, so that is not new. But I don't think that they actually made it work really well so that it was super strong.
Okay, well, I don't want to keep you much longer. I know it's late there. I don't know if people are going to be listening to this long either. But this was incredibly interesting, incredibly helpful, and just gives me a whole layer of new things to think about and talk about with other people. Also, just imagine when I'm doing my own designs and various things. I have a lot of false perceptions of things that I've learned over the years from so many different manufacturers that clearly didn't know what they were talking about. And this helped solve a lot of things in my mind. So thank you so much for this. I hope people listen to the whole thing. I really hope this is as exciting as it is for me for other people. Also, I think that I'm going to try to have Michael Rowland do an interview with you also. He'll do a different kind of interview, which I think would be much better as a counterpart to this one. Not so technical. Okay,
Yeah,
anything else you
I
want to
hope
say?
that, a few things. The basic idea behind this frame was that we wanted to try if a higher resonance frequency would gain benefits when it comes to tuning.
So interesting you say that, because I've just been talking to 3 people about that, because they have more recent frames that they put a set of motors on, and the frame is loud. It's just vibrating to the rotation of the motors and props. And it's just so interesting that you say that, because those are the designs that I'm working on right now, is that I'm looking for a design that's stiffer, that has a higher frequency of resonance, so that it's well above the range of rotation of the props. And
Exactly. That is what.
I don't know if that makes a significant difference in tuning. Conceptually, it makes sense to me, and I think that it would allow us to reduce filters a lot more, because everything would be cleaner, and you would never even hear those higher frequency resonances, because the frame does not resonate below those higher ranges. So it's super
Exactly.
interesting that you say that. Super interesting that you brought that up too. And your A-frame design obviously does that beautifully. Does that very well.
Yeah, we believe it has a resonance frequency slightly over 800 hertz. It depends a little bit on your motor weight and prop weight and so on. I've seen logs with 860 hertz, some with 810 hertz of resonance frequency. So it's really high, because normally frames have around 200, 250 maybe. So and maximum speed of a motor is 450, 500, something like that. So ideally, I want to push it over 1,000. That I don't know if that will. If I know things that can do that, materials that I can improve to push it even higher, but I don't think that the cost will be something that people actually pay for. So I don't know. Yeah, I don't know. But that
So you're
was what
talking
we
about the
wanted to
actual
try.
stiffness, right? The
Yeah,
stiffness of the frame.
yeah, exactly. Because that is what's the stiffness and the weight is what's affecting your resonance frequency. You want a higher weight will lower your resonance frequency. A higher stiffness will increase your resonance frequency. So you want as high stiffness as possible with as low weight as possible. But the problem with high stiffness is that when you crash,
It
you're
breaks.
more
It's brittle.
likely to break. Exactly.
Yeah.
Because as you saw in the list of carbon fiber, when you're going
hmm
up in stiffness, you lose strength.
Right.
And
Right.
when nothing flexes, your forces will get huge. So
Right.
that's why we had to make a frame that is several times stronger
Uh-huh.
with to compensate for this, because otherwise it will fly great, but it will be really brittle when it crashed. So actually, the first prototype flew really good, but it was very brittle. So that was actually what we have been doing or fixing.
Super interesting. This is the same thing that I've been working on in my own designs. That's why I have 2 different primary race design directions, and I can't tell which one is going to work out better. And I'm just going to be putting them out in the community and seeing which one crash tests better, and then just go with that one. Because to me, that's more important than anything, is if it's going to hold up to crashes, and if it's low weight. That's as we said, that's the most important things. And as for the filters, well, the code's really darn good these days, and it can handle most things fine, but still trying to get it to be as stiff as possible is very important. And just
Yeah,
your carbon layup, the way you've set up your carbon layup is already significantly stiffer and significantly just more solid, because of the different strengths of carbon and the different layers that you're using.
yeah, I hope
Hmm.
so. So basically, yes, we can confirm that you need less filters with this, but how much you actually need depends on what gyro you're using, because we've seen huge difference with different gyros. I fly a gyro that needs like one single notch, this dynamic notch, and I can have
Mm-hmm.
one single, not the default Betaflight with 2 notches. So that is very highly filtered directly from the gyro, hardware filtered.
Mm-hmm.
And the very popular MPU 6000 gyro,
Right.
I can't
Yeah.
really
Yeah.
remember,
Yeah.
needs like the one dynamic notch only, and then of course the radix need a lot more because they have way less filtering in the hardware. So yeah, I don't know if that is dramatically differently, but when we started this development, that was like more than 1 year ago. These software that we're using right now, they didn't exist. We had only low pass filter to play with, and then it actually was something really significantly better.
But so one other thing I want to ask, which now you bring up, is so frames that have vertical arms. I've tested vertical arm frames a lot, different designs. I basically can't get away with just using a vertical arm that isn't tied across to the other arms. There has to be some cross bracing of the arm. And what I've discovered is because carbon plate on its side, first of all, most of the noise we get is in the yaw direction because the motors are spinning. Yes. So all the vibration is on the yaw, and that's the main issue. And if you turn a carbon plate on the side, it actually is a lot more flexible than flat-wise for a bunch of reasons. But you get a lot more flexibility in that direction. So when you do get resonance, you get a lot more resonance. And so that's why these frames with vertical plates, vertical arms, need to have some sort of a carbon cross bracing between arms. And so what I have said is that one of the first vertical arm frames that people recognize to be something special is the Talon, the Carrara Talon frame. And yep. I've always imagined or thought and believed that the reason why people think that sounds cleaner or flies cleaner is because it's the cross bracing of the arms that just make the frame much more rigid overall, which reduces the need for filtering and everything else. So everything is running cleaner because of that. It's not necessarily because it's vertical arms. In fact, I've talked to aerodynamics people, and they say vertical arms are actually drastically worse for what we are doing because the attack angle of the arm is not acting like a wing. In fact, at the angles that we typically fly at, it's acting to drag more. It's causing more drag than a flat arm because of the inverse angle of the arm. And so there are some box frames that have these cross bracings it's like a box around the whole thing, and those, in my opinion, because I've built and flown them, they actually do fly differently, but I don't think it's because the box is acting like a wing. I think it's because you have these vertical, like flat surfaces that are helping you in directing your thrust and also allowing you to not slide sideways. Like I'm actually feeling an aerodynamic effect of these vertical plates, but the flat top and bottom are actually slowing you down. So the other thing I've noticed is that when you let off the gas on these vertical box frames, you slow down really extra quick. And that's not a bad thing. It's like having air brakes. Like you can stop and turn immediately. And so people in your side of the world, Sweden, they actually love these box frames, right? Is that why they love those things? Popular. Very, very popular. Yeah. And I would say that's a very correct reason. I think that they should be very popular, but in my opinion, they're a little bit more complicated, and in America we're not so happy about complicated things. We like simple we like live rear axle cars and like simple stuff. So that's why most of our designs are still just traditional arm designs, nothing special, with fewer parts and fewer management of things. So you've taken it to the next step because you're taking the complexity way up a notch in all respects, in the engineering, in the design, in the substructure, all of it together.
There are not more parts in this design than box frame.
Typical,
it's actually
right. Yeah.
It's the same amount of parts. It's just totally different. And what we started off with a box frame that was what we liked, that we think was the best design when we started this project. But we were well.
You what? Where'd you go? Did your phone run out of batteries? Hello? Hello, hello, hello? Hello? Hello, 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 hello? Oh, well, I'll stop it for here. I think that's enough for now. When I actually get the frame and I review it, I talk about it. We'll talk about this more. I'm gonna interview Johan some more. But yeah, I think, yep, yeah.
What
So that's all for
happened?
now. Oh, hey, you're back. I was gonna say that
My headset
it's
just dropped. I don't know what happened.
whatever it is. Let's do another interview when the frame is more available. I don't think people are going to listen to 2 hours of interview.
No,
so,
I don't think
so yeah, I'll talk to you more about it later. Go to sleep. Go to sleep. I'll talk to you later. Okay.
Take care. But I do want to listen for this before we.
Yeah, definitely, absolutely, absolutely. I'm gonna edit it right now and I'll put it up for private, and you can listen to it before anything else, and you can watch it and everything before. Okay.
Okay.
Thank you so much. Thank you so much. Take care. Bye.
Bye bye.